Mathematics in Lambda class. In this episode, we're going to discuss groups, actions, and the Lagrange theorem. Okay, so groups are a very important mathematical structure in classical and modern mathematics, and they appear everywhere, and we have been using groups without naming them for quite a bit now. Actually, groups are used to describe very ordinary situations and also very sophisticated ones. Okay, so let's start with the definition of what a group is. And this is one of the most useful mathematical entities that you can come across. So let G be a non-empty set such that it is equipped with an operation phi. It takes two elements of G and returns another element of G, usually phi of G and H. We're gonna use Polish notation, and this is gonna to be G star H. This is going to be the notation that we're going to use to describe the image of phi applied to G and H, such that okay, the first thing we're going to require, there exists an element E belonging to G such that E against H equals H star E, and this is H for every H in G. Second of all, phi is associative. That means that whenever you need to make this operation, this equals G star H star K, and for each G in G, there exists G tilde such that G star G tilde equals G tilde stars G, and this is E. Okay, this element E, this distinguished element E, is called the neutral element for phi. E is the neutral element for phi. This is called the group operation phi, and the group operation has a neutral element called E. It's sometimes it's also called the identity for the group operation. Then phi is associative. We can associate. That means that we can use parentheses however we like. And finally, this G tilde accounts for the inverse respect to the group operation. G tilde is the star inverse of G. All right, so there are many examples for this, and they are all very well known for us. Examples. Okay, the first example we're going to show is the integers and the star operation simply take addition. We are going to say that G star, this tuple, is the way we are going to know groups. In this case, it's C with addition. Okay, addition is obviously associative. Okay, in this case, the neutral element is 0, and the inverse for G is actually minus G. Okay, this is example 1. We observe that in this example, the group operation is also commutative, which is not required by the definition. Okay, the definition just requires phi to be associative. Okay, but in this case, it is also commutative. Observation: groups with commutative phi are called abelian groups, also called commutative groups. Okay. Second example, example 2, right? In this case, let's take G, the real numbers minus 0, is R minus number 0, okay? So this is a subset of the real numbers. And the star operation is going to be simply multiplication. Standard scalar multiplication. Now in this case, the neutral element is going to be just the number 1, since 1 times x equals x for every real number x. And the inverse of G is simply going to be 1 over G, also noted G to the minus 1. Okay? So the multiplicative inverse is just the reciprocal of G. And this can be taken since every G is non-zero in G. Okay? So these are 2 examples in which the group operation is commutative. Well, it is not the case that every group is commutative. Example 3. Let's get to a more involved example. Let X be a non-empty set, and let's take S of X, simply the functions from X to X that are bijections. Okay, bijections are functions that can be inverted. Okay, so this is going to be our underlying set for the example, bijections from X to X. And now the star operation is going to be function composition. In case you don't remember, if f and g are 2 bijections, or 2 functions in general, the composition of f and g applied to an x is defined to be f applied to the image through g of x. Okay, and now the underlying set with the composition of functions yields a non-commutative group, that is a non-abelian group. Okay, composition, this turns out to be a non-commutative group. Let's show with an example that this is the case, but you know, in this case, the neutral element is simply the identity. This is the function identity x is the function that simply takes an element of x and leaves it quite over there. It's identity function. So composition of function is not commutative, and here the neutral element is simply the identity function. Let's make an example of this example. So example 3b. 3b. So to fix ideas, let x be the set 1, 2, and 3. So S of x just consists of the bijections from x to x. Okay, maybe we can list which are the elements of S of x. First of all, the identity element is the function that takes 1 to 1, 2 to 2, and 3 to the number 3. So this table portrays the identity element. Okay, it's a correspondence between elements of x and elements of x. Maybe you can think of it as a reordering of 1 to 3. Okay, so what else? Well, we have another table, maybe the function that sends 1 to the number 2, and then 2 to the number 1, and then 3 to the number 3. This is another element of S of x, since this is a bijection. Now this function takes exactly the set 1 to 3 to the set 1 to 3. Simply a reordering. Let's go and find another one. Maybe the element h will take 1 to 3, 2 to number 2, and 3 to number 1. This is yet another one of the elements of the S of x. And maybe there's another one, right? Maybe we can find more. And in this case, it's not that complicated. Maybe the one that says 1 goes to 2, and then 2 goes to 3, and then 3 goes to 2, to 1, I'm sorry. Let's call it K, and let's go and draw another one. We're closer to the end. 1 goes to 3, then 2 goes to 1, and 3 goes to 2. Let's call this one L, and let's go for the last one. Okay, so what else? We have the ones that fix 3. We have we need the ones that fix number 2, right? So this is M. Then we need so we have 2 that fix number 3, 2 that fix number 2, and we need the ones that fix number 1. Okay, so 1 goes to 1, 2 goes to 3, and 3 goes to 2. And this is it. S of x is the set of functions, these 6 functions. S of x consists of the identity f, h, k, l, and m. So we say that S of x has exactly 6 elements. This is a finite group because it has a finite number of elements. So we will show now that this is a non-commutative group using composition. Let's show with an example. Then S of x with composition is not commutative. Let's take, for example, the last two. Let's take L and M. Let's see if this works. Now, okay, so let's try to compute the composition of L and M. First of all, let's try to figure out what L composed with M is, right? So in order to see what a function is, we need to learn what it does to each and every element of x. So what does L composed with M do to number 1? Well, first of all, M takes number 1 and then spits out number 1. And now L takes number 1 and spits out number 3. So we have that 1 goes to 3. Now let's see what it does to number 2. So M takes number 2, produces number 3. Then L takes number 3 and gives back number 2. Okay, so finally, M takes number 3, spits out number 2. L takes 2 and spits out 1. So this is the effect of actually composing L with M in this order. If you take a look, L composed with M ends up being H. Observe that L composed with M gives H. It's another element of the group. Yet, what happens when we do it in the opposite way? Now, we take number 1, give it to L, then L spits out number 3, and M takes 3 and spits out 2. Then number 2, give it 2 to L, L spits out 1, M takes 1 and spits out 1. Finally, we take 3, we give it to L, L hands out number 2, and M hands out number 3. So in this case, M composed with L ends up giving simply F. M composed with L gives F. In any case, since these tables are different, we conclude that M composed with L is different from L composed with M. That means that S of x with composition is not a commutative group. It's not a commutative group. Okay, so this is a finite group which is not commutative. Before we've seen infinite groups. Since this is an infinite set, and this also is an infinite set. So groups can be finite, infinite, commutative, or non-commutative. There are many flavors of groups. Okay, so this set is called the set of transformations of X. observation. Observation, this is very important. If X is a non-empty set, S of X is called the set of transformations of X, and or also the set of symmetries. Of X. Okay, we're going to use this many times. Okay, so it's a very important example. Some observations for groups. First of all, the identity element is unique. There's only one element that can act as an identity. Suppose E and E prime are identities in a group G, then they're the same. And the proof is very simple. Proof. So if E is the identity, then E times E tilde E prime has to be E prime, right? But if E prime is the identity, then E times E prime has to be E. So this leads to E prime equal to E, which is kind of obvious, right? Secondly, for G in G, there's a unique inverse G tilde. That is, if two elements act as the inverse of G, then they're the same. That is, if G tilde and G tilde tilde are both inverses for G, then they coincide. And the proof is also kind of similar. Proof is similar, right? Because we need to show that these two elements are the same. So what we can do is we can express G tilde as G times E, the identity. And now we can express the identity as, I have written times, but we can read it as star. And we can express this as G star the inverse G tilde tilde. And now, since the operation is associated, we can associate this like this. And now we're going to use that G tilde is the inverse. So this gives E star G tilde tilde, and since E is the identity, we derived that G tilde has to coincide with G tilde tilde. So they're the same. Inversors and neutral elements are unique in a group, okay? And this comes from the possibility of having an associative operation like star, okay? Observation. There are mainly two notations. We use plus for commutative groups. And we use dot for not necessarily commutative groups. So it's way easier for us to use the dot notation. The star symbol is kind of complicated sometimes. So from now on, we're going to stick to the multiplicative notation, and that does not mean that we're talking about commutative groups. Multiplication will cease to be commutative unless specifically said. Okay? So there are plenty of examples of groups. We just talked about transformation groups, and we have talked about the integers with addition and non-zero real numbers with multiplication. Okay, but there are many, many others, right? Let's talk about subgroups. So a subgroup. What is a subgroup? Okay, a subgroup is a group within a group. Okay, let G be a group. Okay, we say that a subset H is a subgroup of G, and we note it H less than G if H with the dot is itself a group. This is a non-trivial observation. The observation here is that this operation, this dot, is defined as a function that takes two elements of G and produces an element of G. So this, as a function, has domain G times G. If you think of the domain of the dot, it is simply G times G. This is the domain of the dot, the original dot that was assigned for G. So what does it mean that H and dot is itself a group? This means that since H is a subset of G, this is H and this is H, then dot restricts to H times G nicely. This means that dot will take two elements of H and produce an element of H, not only an element of G. It will produce an element of H. Okay, so we're going to state this in a concise way, giving a more common definition, and we will see one of the consequences of the definition, and we're going to place some examples of H, and then we're going to note something that's very important for us. Okay, we're going to talk about group actions once we define subgroups and group morphisms. So H as a subset of G is a subgroup if, well, first of all, the identity element of G needs to belong to H. So this also means that H is a non-empty set. 2, whenever H1 and H2 belong to H, then their product also belongs to H. 3, each time H belongs to H, then its inverse also belongs to H. These 3 conditions are the usual definition of a subgroup of G. Okay, it needs to contain the identity element of G, which means that whenever we want to think of the identity of H, it's simply the identity of G. Okay. Each time we take 2 elements of H and multiply them together, we also get an element of H. That means that dot restricts nicely to H, cross H, and the inverses also. Okay. Since H is in H and also an element of G, then the inverse of H lies in G, but also in H. So taking a look at the inverse of H in the smaller group is actually the same as looking at it in the bigger group. Okay. Being a subgroup is being a substructure. Okay, so everything we say for groups holds for subgroups. So there's no problem there. Okay, let's take a look at some examples. Examples of subgroups. Examples. Well, if we go along the same lines that we went before, let's take the ambient group of being Z, and let's take H to be even numbers. In this case, we will describe H as things of the form 2 times L for L in Z. Okay. And here the operation is obviously plus. So why is it that H is a subgroup? Well, this is fairly trivial. Let's prove that the identity element for G, that was 0, belongs to H. That's obvious, since 0 is actually 2 times 0. Okay, that's easy. Let's see if H1 and H2 belong to H. We need to show that their sum, here we're using additive notation, remember that their sum also belongs to H. And that's obvious, because the sum of 2 even numbers is also even. So H1 is of the form 2 times L1 for certain L1 in Z. H2 is 2 times L2 for certain L2 in Z. And so the sum 2 times L1 plus 2 times L2, and this is 2 times L1 plus L2. And since this is an integer, because the sum of two integers is an integer, this says that the sum belongs to H. So H is closed under addition. Okay? And lastly, if H belongs to H, then its inverse, minus H, also belongs to H. Okay? And this is easy, because minus H is minus 2 times L for certain L, and this is 2 times minus L. And since this belongs to Z, this belongs to H. Okay, so actually H is a subgroup of the integers. So we have shown that this is a subgroup of a commutative group, infinite commutative group. Okay? So basically we have three things to check. Let's make a more involved example. Example 2. Example 2. Let's fix x as a set 1, 2, 3, and 4. Okay? And in this case, we have the group of transformations for x, that is the bijections from x to x. The operation is going to be function composition, right? And let's take a look at the functions from x to x, such that f of 1 gives 1 and f of 3 gives 3. Okay? We need to show that this is actually a subgroup of G. We'll show that H is a subgroup for G. All right. So why? How come? Well, first of all, the identity element in G is simply the identity of X. And the identity of X fixes every element of X. In particular, the identity applied to 1 returns 1, and the identity applied to 3 returns 3. So that means the identity is an element of H. So the neutral element for G also belongs to H. That's easy. Now, let's take F and G belonging to H. We'll need to show that the composition also belongs to H. And that's easy, right? Because all we need to do is we need to see what this composition does to number 1 and what this composition does to number 3. By definition, this is F applied to G of 1. And since G belongs to H, G of 1 needs to be 1. And since F belongs to H, F of 1 needs to be 1. So the composition fixes 1, since 1 to number 1. By the same token, composition also fixes 3. So the composition fixes 1 and 3, then the composition belongs to H. Finally, if F belongs to H, then we need to see if its inverse belongs to H as well. Okay. So what do we need to check? We need to see what does the inverse do to number 1 and number 3. But that's easy. Since f of 1 is 1, applying the inverse to both sides. And now using the definition of the inverse, right? This is simply f composed def at 1. And this function is actually the identity applied to 1. And the identity applied to 1 is simply 1. So what we have shown is that the inverse of f applied to 1 gives simply 1. We have shown that the identity and the inverse of f also fixes 1, and by the same token we can show that the inverse of f also fixes 3, and that means that the inverse of f belongs to H as well. Since the element f in H was generic, then H ends up being a subgroup of a non-commutative group G. All right? That's awesome. Okay, so we have one more example of a subgroup, which is an important example. Important example. Okay, having defined groups and subgroups, we're gonna take a look at what sort of functions are going to allow, are we going to allow between groups? And that requires that we talk about group morphisms. So a group morphism is a function between groups that is compatible with the group operations. So let G1 with star 1 operation and G2 and star 2 operation be two groups. A group morphism f is a function. It's a function f that goes from G1 to G2 is simply a function such that whenever we apply f to G1 star 1, let's change the notation, G star 1 H, this is equal to f of G star 2 f of H. Okay, this is what a group morphism from G1 to G2 is. First observation is this operation is performed in G1. In G1. We take two elements of G1, okay, and star them together with the operation native in G1. When we push that to the right, we get two elements of G2 that get operated in G2. So this operation takes place in G2. So F is compatible with the group operation. F transforms operations in G1 to operations in G2, right? That's what a group morphism is. Usually, observation, if context is understood, we will always have in mind that these operations are different. And we may use the same symbol for them, always taking care and keeping in mind that these are different operations performed in different uh, uh, environment sets. So we say that f applied to g times h is actually f of g times f of h. This dot here is different from this dot here. They're different. Dots. Okay, so this will alleviate the notational burden sometimes, but it's fairly easy to work with morphisms once we understand that difference. Now, keeping the notation simple is key for us. Okay. Some observations and things that we can deduce from the very definition, from the definitions. Okay. Also, we'll use E for both inverses. Okay, for both neutral elements for G1 and G2. Okay, the first of all, we are going to show that if F is a group morphism, then F of the neutral element of G1 has to be the neutral element of G2. Okay, this is something we need to show. All right, and how do we do that? Neutral element goes to neutral element. How come? Well, the neutral element, when you act it on itself, it gives itself the neutral element. Okay, this identity is trivial since E1 is the neutral element of G1. So when you apply F in both sides, and you use that this is actually a group morphism, what you get here is that F of E1 applied to F of E1 has to be F of E1. So since F of E1 is an element of the group G2, it has an inverse. Let's call it, I don't know, maybe let's call it K. So if we act K on both sides, and we associate now K times 1 acting on F of A1, since K is the inverse, this is actually E2, and this is actually E2. And since E2 is the identity or neutral element of G2, this is actually F of E1. So we landed where we wanted to land. F takes the neutral element of G1 and maps it to the neutral element of G2. All right. So for a function, in order to be a group morphism, it needs to take neutral element to a neutral element. All right. Second, well, it also behaves well under inverses, right? F of the inverse of an element H needs to be the inverse of f of H. Okay, this is also easy to show, right? Since the inverse of H times H, this is the neutral element of G1, applying F on both sides gives F of E1. We have shown that this guy over here needs to be the neutral element of G2, and since F is a morphism, F applied to the inverse of H applied to F of H gives this. But then, since inverses are unique, we know that this guy shows, plays a role of the inverse of f of h. Then it is the inverse of f of h. The inverse of f of h has to be f of the inverse of h. So group morphisms are compatible with the group operations, okay? They are compatible with the group operation. And that means that they need to take the identity to the identity and the inverse to the inverse, okay? Not only to the operation itself, but it respects neutral elements and inverses. So group morphisms are a very nice thing to work with, and there are many theorems about group morphisms. Okay, but we're going to talk about something specific that we have in mind. Maybe we can have some examples before, but let's go deeper now. Let's talk about group actions. Let's get serious. Let X be a non-empty set. And let G be a group. Let H be a group. Be a group. We'll say that H acts on X if there is a group morphism psi that takes elements of H to elements of the transformation group of X. That is, to each element of H, what we have is a bijection from X to X. So we have a way of identifying elements of H with bijections of X. And that is what we call a group morphism, a group action. Notation: when psi is understood, or implied, we simply write that H acts on X using psi. Okay, this letter is usually omitted and we just keep this notation for H acting on X. Okay, so there are many things to say about actions. We're gonna go deeper in a different video, but we need to say one thing. Whenever we have an action, we're gonna have an equivalence relation on X. Observation / theorem. If a group H acts on X, then we have an equivalence relation on X. X will be H related to Y if and only if there exists a small h such that phi h takes X to Y. Okay, so this is the definition of an equivalence relation, and we're going to show that this is an equivalence relation. Okay, some notation. The image through 5 of H is actually phi of H. Yeah, phi of H. This is a bijection, is a bijection from X to X. So this is a function. It's an element of G, an element of H, and the image is actually a function. And the notation that we're going to use, this function applied to X, X is an element of big X, this will be noted H acting on X. And this will sometimes have the phi. In some texts, that phi is omitted because it is understood that this is an element of a group and this is an element of a set. Okay, there are not two elements of a group. Okay, so once we have clear in our heads that there's a difference between those two dots, we can go along and play the game. But if we're not used to it, we need to use this sub psi over there, right? So let's show that we have an equivalence relation, and we're going to show that for a certain action, that equivalence relation yields what we call the Lagrange theorem. Okay, so let's show proof. Let's show that this is an equivalence relation. So to show that this is an equivalence relation, we need to show three things, okay? first of all, we need to show that this is reflexive. Well, and that's easy because the identity acting on X is simply phi of the identity applied to X. Okay, but we have said that psi is a group morphism. So this function needs to be the identity of X. So this is the identity of X applied to the element X, and the identity of X yields X. So what have we seen? We have seen that the neutral element of H acts fixing X. So this means that X is related to itself. Okay, and we have seen this because a group morphism sends the identity of H to the identity of the transformation group SOX. That's the first part. Now let's show that this is symmetric. So we need to show that this relation is symmetric. Okay, so let's suppose that X is related to Y. That is, there is an H in the group such that H acts on X and yields Y. All right, so we need to show that there's another element, okay, that there's another element of H that takes Y to X. And since these are two elements of X, what we can do is we can apply, since they're the same element, we can apply a different function. So let's use H to the minus 1 to act on this element. So what are we going to do? We're going to make H to the minus 1 act on this element. So that is H to the minus 1 is acting on Y. Okay, so if you take a look at this, what does this mean? This is phi sub H to the minus 1 applied to the element H acting on X. Okay, but what is this? This in turn is actually phi corresponding to H to the minus 1 applied to phi corresponding to H applied to X. And this is actually a composition of functions. This is this function composed with this function applied to X. But psi is a group morphism. So this ends up being what? This ends up being psi of H to the minus 1 times H acting on X. All right. We can show, maybe we can, this is not the right notation. This is simply, let's use it like this. This is psi at h to the minus 1, composed with psi composed with h. And now we use that psi is a group morphism, and this is simply psi applied to h to the minus 1 times h. So this is almost here now, because since these two guys are inverse to each other, this is psi applied to the identity element. And this has to be the identity element of the transformation group. So this is the identity of X acting on X. And the identity of X acting on X is actually, what do we need to say now? Here it's, I'm missing this parenthesis over here. And this is simply X. So we have shown that if H takes X to Y, then H to the minus 1 takes Y to X. And that means that Y is H related to X. So this means that this relation is actually symmetric. Whenever we have X related to Y, we also have Y related to X. All right? And lastly, 3, this relation is transitive. Suppose that X is related to Y, and Y is related to C. Then we need to show that X is related to C. And this is simple. This is simple. What does this mean? Well, this means that there exists H1 such that H1 acts on X and returns Y. And what does this mean now? This means that there exists H2 such that H2 acting on Y gives Z. And this is easy now, because H2 acting on Y returns Z, and now we can write H2 acting on H1 acting on X. And this is simply H2 times H1 acting on X, and this is C. Okay, so here we have it. X is related to Z through H. So what we have now is an equivalence relation. Is an equivalence relation. And this means that we have orbits. The equivalence class under this relation for an X belonging to X is called the orbit orbit of X. The equivalence class is called the orbit of X, and it consists of all the elements of X such that H acting on X returns Y. All the things that can be reached moving X using elements of H. All right, so that's very important for us. This is the definition of the orbit of X, right? And to conclude this video, we're going to talk about something important. That's the Lagrange action. So let G be a group, be a finite group, and let H be a subgroup. It doesn't really matter if G is commutative or not. What's important for us is that G is a finite group and that H is a subgroup. So let's take a look at the following action. The action is going to take an element of H, and it's going to do the following, okay? We're going to take a look at the bijections of G, okay, bijections of G, that are defined this way. So if you take an H, you're going to take a look at this bijection. The bijection corresponding to H takes a G and it multiplies G to the left by H. So it can be checked that this psi is an action. This is H is acting on its ambient group. Sometimes they say by translation on the left. You multiply it using the small h to the left of G. These are bijections. These are a claim that is very simple to define, to prove. First of all, phi sub h is a bijection for every h in H. That's an easy claim for you to prove, and it's easy to show that psi is a group morphism. And that's easy since psi of h1 times h2 is a function that takes elements of G to elements of G. And we're going to apply it to G. And what it does is multiplies G using this element. Okay, so now what we have here is that this multiplication is simply taking, by the definition of psi, this is taking the element h1 times h2 and use it to multiply G to the left. These are all multiplications in G. These dots are all multiplications in G, right? And now we use that multiplication is associated, right? So this is h1 multiplying these two guys together, right? And this is simply psi of h1 applied to psi of h2 applied to g. And this is simply this function composed with this function applied to g. So what we have shown is that this is essentially this composition. So psi is in effect a group action. See, this is called the Lagrange action. Of H on G. Okay, and this action will define a partition. This action defines a partition of G into disjoint equivalence classes, disjoint orbits. That means that G can be thought of as the union of finitely many classes. Now, since G is finite, each orbit is finite, each OX is finite, and also there are finitely many classes. So this means that if we think of G like this, then we have finitely many classes. Class corresponding to G1, G2, G3, G4, the class of G5, the class of G6, etc. But with one a very interesting observation. In general, orbits for a general action, for a generic action, they're different. And specifically, they have different sizes. But for the Lagrange action, if you take a look at it, the orbit of G is actually all the elements K belonging to the group G, such that there exists an H in H that acting on G give K. But this action is actually group multiplication for the Lagrange action. This is simply the group operation. So the class of G is actually the set H times G. And we are meaning all the things of the form H times G for H in H. So this means that whenever we take an element of G and take a look at its orbit, the orbit of G, it's always of this form. The orbit of G is H times G. So this means that the amount of elements in a orbit of G is actually the number of elements in here, and this is actually the number of elements of H. And this is crucial. Each orbit has number of elements of H elements. So going back to the partition of G, G can be thought as a finite number of orbits, and since this union is disjoint, the number of elements of G is actually the sum of the number of elements in each orbit. And all these guys are the same. They all have the same number of elements. So this is simply n times the number of elements of H. This natural number n is called the number of orbits. It's called the index of H. Index of H in G. It's the number of orbits that appear when we take a look at the Lagrange action. Okay, so this is written like this. The order of G is the index of H in G times the order of H. And this is what we call the Lagrange theorem. Okay, this is what we call the Lagrange theorem. It simply states the following. If G is a finite group and H is a subgroup, then the order of H divides the order of G. The order of H divides the order of G. So subgroups are very special objects, okay? Since they need to be closed under the group operation, they need to be closed under taking inverses, and they need to contain the identity element, they cannot have any shape without structure. All those constraints make subgroups very special subsets. They need to contain a number of elements that necessarily divide the number of elements of the ambient group. Okay? So this is a very powerful theorem, and since there are many things that qualify as finite groups, this theorem takes different forms, okay, and will give us lots of information in very different contexts, and we're going to use that soon in order to talk about field extensions. We're taking this detour, this maybe long overdue detour into group theory, because when we want to play with Starks and we need to choose a domain size to perform some proof checking, we need to do that in a very smart way, because we have described how the Stark protocol works, but that's a good theory. How do we implement that? How do we tell if we can find a polynomial that actually does what it promised it does? Well, the number of elements in a domain has something to do with it, because when the number of elements in a domain is a power of 2, then we can have a good and fast strategy to solve the problem. Okay, so we're going soon to be joining this idea of playing with groups, with the idea of extending a field, with the idea of solving the Stark's problem in practical terms in a fast and efficient way. We will need elements of Fourier transform, and we will need more elements to this. But the choice of the domain size to perform Starks is not something easy. We need to choose a domain size that will enable us to perform that calculation and that verification quickly. In order to do that, we need to learn some things about group extensions and field extensions as well. So this is it for now. Let this sink. We're going to go through a bunch of examples in the following videos, and we're going to take this long turn, this long curve, and we'll rejoin Starks in a couple of videos time. Okay, thank you for watching, and feel free to watch again as many times as you want. Okay, goodbye.